Hello everyone, welcome to this session. Before starting today's session, let us have a quick recap of what we studied in the last class. If you recall, we started with V notch. So I said triangular notch is also called V notch because this triangular notch is in the form of V. That's why most of the time these triangular notches are called V notches. I said we have 30-degree V notch, 45-degree V notch, 60-degree V notch, 75-degree V notch, 90 and in some cases even 120-degree V notches. Then we also discussed about the advantages of why these V notches are preferred over other notches. I mentioned about 3 advantages. One is the discharge equation for this V notch is very much simple compared to other notches. If you kindly recall, in the last class, if I presume the value of theta is equal to 90 degrees, then in the discharge equation tan theta by 2 is equal to 1, that is one condition. And suppose if I assume the value of CD is equal to 0.62, then if you simplify that equation, okay, you are going to get that Q is equal to 1.417 h raised to 5 by 2. What I mean to say here is, if at all if you want to measure the discharge in a channel, if you just measure the head over the V notch, that will be more than enough to calculate the discharge. That is the beauty of this V notch. I also said another thing which is very, very important. I asked you to write the general V notch equation or triangular equation. What it says, Q actual is equal to 8 by 15 CD root 2G tan theta by 2 into h raised to 5 by 2. Never ever write the simplified form. Very, very important. Then we discussed about simple problems on this V notch. Then we moved on to trapezoidal notch. So I said trapezoidal notch consists of a rectangular notch plus a V notch. We already derived an equation for this rectangular notch and a discharge equation for a triangular notch. So if you club these two, you are going to get a discharge equation for a trapezoidal notch. Then we moved on to Cipolliti notch. If you recall, I said Cipolliti notch is a type of trapezoidal notch where we do not have end contractions. How you are going to maintain that, or how we are going to see that there are no end contractions in a Cipolliti notch? So in that case, the side slopes you are going to provide is for every one h. For every one horizontal, there is 4 vertical. Very, very important. 1 is to 4. H is to V is equal to 1 is to 4. So in that case, my value of theta by 2 works out to be 14 degrees. Or if you talk about the apex angle, my theta works out to be 28 degrees. Then the equation reduces to 2/3 CD root 2G L h raised to 3 by 2. That is the same discharge equation that holds good for a rectangular notch without end contractions will be the discharge equation for this Cipolliti notch. Then we solved a simple problem on this trapezoidal notch and Cipolliti notch. That is the point where we stopped in the last class. Let us move further. There are 2 more type of notches which are not so popular, but anywhere as a civil engineer you need to know this type of notches. One is a stepped notch, the other one is what is known as a sutro notch or a proportional wear. So let us first talk about this stepped notch. If you look at the figure, okay, basically it is a combination of rectangular notches. If you talk about this is one rectangle, this is another rectangle, this is another rectangle. So you have a combination of rectangular notches. So the discharge through the stepped notch is equal to sum of the discharge through different rectangular notches. Okay, it is very easy to find the discharge through the stepped notch once you know the discharge through a single rectangular notch. Now, how to find an equation for this stepped notch? So for that, so let us consider this figure here. Okay, so if I call this, that is from the first step to the free surface as H1, from the second step to the free surface as H2, from the sill to the free surface I call this as H3. Now based on this, so H, the height of water above the crest notch 1, L1 is the length of the notch 1. Similarly, H2 L2, H3 L3 are the corresponding values for notches 1, 2 and 3 respectively. Presume that the coefficient of discharge for all the 3 notches, that is equal to CD. What is the total discharge? At the beginning I said the total discharge through the step notch is equal to discharge through first rectangular notch, discharge through second rectangular notch and discharge through third rectangular notch. If you sum up these 3, you are going to get the total discharge through the step notch. That's what I did in the next step. If you look at that, so what is the discharge equation for a rectangular notch? 2/3 CD root 2G LH raised to 3 by 2. This is the equation what we derived in the last class. Okay. If I don't consider the end contractions. If I consider the end contractions, then you need to correct for L. So how you are going to correct for L? L minus 0.1 NH. Okay, what is that N? N represents the number of end contractions. Kindly recall, I said for a rectangular notch there are 2 end contractions. In that case, if you account for end contractions, in that case my length of the crest becomes L minus 0.2 H. Okay, in this case, in the present case, okay, so I am not considering the end contractions, therefore the discharge equation is equal to 2/3 CD root 2G LH raised to 3 by 2. Now look at this. So here H1 is the height with respect to the first notch, H2 is the height with respect to the second notch. So H1 raised to 3 by 2 minus H2 raised to 3 by 2. Come to the second notch. So here, so there is kindly correct me. Here this plus has to come here. Kindly make a correction here. So 2/3 here. So plus you put this plus here. It is 2/3. This is for the second rectangular notch, that is H2 minus H3. Now when you come to the top one, it will be 2/3 CD L3 or root 2G L3 into H3 raised to 3 by 2. If you simplify this, or if you keep it as it is, depending on the data given in the problem, if you substitute the values, you are going to get the discharge through this stepped notch. Clear? So again I repeat, whenever I am talking about a stepped notch is a combination of rectangular notches. If you know the discharge equation for a rectangular notch, then the total discharge is equal to, so this Q1 plus Q2 plus Q3 up to Qn. Okay. Now you need to define this H and L for each and every notch. Then accordingly you need to substitute the values in the general discharge equation and simplify, or if you substitute the values in the equation, you are going to get the total discharge. This is how you are going to find the discharge whenever you are using a stepped notch. I hope it is clear. Then kindly recall, when we were discussing about the orifice, okay, we discussed about the same topic. Suppose if I consider a tank with certain depth of water, suppose if I provide an orifice at the side or at the bottom of the tank, in that case in the derivation what we derived there, I provided the orifice at the bottom of the tank. The question I asked is how much time I required, for the orifice to empty the tank. Or the other question is, other way of putting that is, suppose in a time t, what is the drop of fluid from H1 to H2? I repeat, so you have the orifice, you know certain depth of fluid in the tank. The question I am asking is, in time t, so what is the drop in the fluid level in the tank? That is the first question. Suppose the next question is, how much time the orifice will take in order to empty the tank? This is what we studied in the orifice. Similarly here also, so you have a channel or a tank. So suppose if you provide with a rectangular notch, okay, how much time the notch will take in order to empty this tank or a reservoir? So for that, so consider a tank or a reservoir of uniform cross sectional area A and a rectangular notch provided on one of its side. Okay, let L length of the crest of the notch. Before this, kindly recall the discharge equation for a rectangular notch without end contractions is equal to 2/3 CD root 2G LH raised to 3 by 2. This is the formula I am going to use right now. So for that, what you need? You need the length of the notch. Remember the length of the notch in the last class I told you several times. So once you fabricate the notch, it won't change from trial to trial. It is fixed. So that's why we define this length L is equal to the length of the notch. Then I defined another two terms. One is H1, the other one is H2. What is H1? So suppose if this is a sill level. So okay. So before water starts flowing over the notch, so you have this head. So that is this vertical height is H1. Then in time t, how much drop of water will be there from H1 to H2? So that's what I defined here. So here H1 is the initial height of liquid above the crest of the notch, and H2 is the final height of water or liquid above the crest of the notch. Now, in order to drop this fluid from H1 to H2, what is the time required? That time required I defined it as capital T. So T is equal to time required from again correction kindly from H1 to H2. Now at any instant, suppose the water level is at H1, immediately you open the rectangular notch and water level starts falling. Now at any instant, the height of water surface above the crest of the notch BH. Okay, so that's what I mentioned here in a small time dt. So in that case, the liquid surface falls by dH. What it means? I have this. So this is a sill level. This is H1. I open the rectangular notch. Water starts falling. At any given instant t, I consider a fluid layer. So at that fluid layer, in time dt, it falls by dH. Okay. Now, in that case, the area is given by A into dH, that is equal to Q into dt. What is this? Why if there is a minus sign? Minus sign is taken as with the increase in T, H decreases. Remember, if you allow more time, naturally my water level from H1 to H2, it goes on increasing. So that's why we put that minus A there. So here, so minus A into dH is equal to Q into dt. Clear? Now, this discharge equation is given by 2/3 CD root 2G LH raised to 3 by 2. Now, this is what I explained here. Now, here this is H1. Okay. Now, here suppose somewhere here if I consider as H2. Now, if this fluid falls from H1 to H2, how much time it requires? That is capital T. That is one thing. Now, at any given instant, okay, at a depth h from the free surface, okay, I consider a small strip having in time delta dt. So it falls by delta h. Okay, with that we started deriving the equation. Now look at this. Q is equal to, so 2/3 CD root 2G LH raised to 3 by 2. Now we know this already, we derived this, minus A into dH is equal to Q into dt. Now in place of this Q, you substitute this equation. It is a very simple derivation. Okay, so minus A into dH is equal to, so this is discharge. Remember, discharge as a unit of meter cube per second. If you multiply that by second, automatically this you are going to get volume. Now you come to the left hand side. So this is area into the depth of the fall in water level in a very short interval of time dt. Therefore, suppose if you, so this is meter square, this is meter cube, again volume, and on the right hand side also you have this volume. Now basically I am looking for this dt. Okay, so what is your aim? Your aim is to find the value of capital T. How much time it is required for the notch to empty from H1 to H2. That's our aim. That's how we started deriving this equation. So therefore dt is equal to, simplify this equation, minus a dh divided by this entire equation. Now I need the total time. So in order to get this total time, I need to integrate this equation between the limits. So what is the limit? When my time is equal to 0, the level of water is at h1. I hope all of you agree with me. If I don't open the rectangular notch, what is the initial height? Initial height, we represented this as h1. So after the time t, capital T, so what is the level? Level is h2. So what is the limits for this t? So t, my t varies from 0 to capital T. That's what I put it on the left hand side. So integration of dt with limits 0 to capital T, that must be equal to, come to the right hand side. So here what is the limits? So initially my water level is at h1 and so the final level is h2. Okay. So put that limit, and if you integrate this and simplify this, you are going to get an equation for this t, that is this t is equal to 3 into a divided by CD into L into root of 2g divided into 1 by root of h2 minus 1 by root of h1. Okay. Now let us spend a few seconds on this. So what is this A? A is the area of the flow section. So when I am talking about a rectangular section, what is the area of a flow section? It is the length into the depth of flow. That's about A. The length is constant. I said once you fabricate, okay, length won't change from trial to trial, that is constant. Root 2g is constant. What is the variable? The variable is h1 and h2. Your h1 may be 10 centimeter, h2 may be 2 centimeter. Or you want to empty that entire tank. In that case, my h2 is equal to 0. Okay. So this is how you are going to use this equation in order to find the time taken by this notch in order to empty a tank or a channel. Okay. I hope this is clear. If you look at previous question papers, or if you take out any textbook, you are going to see this heading very important. What is this heading? Effect on discharge over a notch or a wear due to error in the measurement of head. Now before actually start this topic, let us look into, we derived 3 equations. First we started with the rectangular notch. Let us know the discharge equation for a rectangular notch. Q is equal to 2/3 CD root 2g L h raised to 3 by 2. Kindly recall 2/3 CD root 2g, L is a constant. In that case, my Q is equal to K into h raised to 3 by 2. Or if you go one step further, your Q is proportional to h raised to 3 by 2. What it says? The discharge that is flowing over the notch is directly proportional to the head you are going to measure on the notch. So then what is the big deal? The big deal is, if you do a little mistake in noting down the head over the notch, it will have a cascading effect on the value of Q. So again I repeat, if you do a little or a mistake in noting down the head over the notch, then the actual value of the discharge varies. That's why noting down the value of head over whether it is a rectangular notch, triangular notch or a trapezoidal notch or a Cipolliti notch is very important. That is what we are going to see in this section. Okay. Now again talk about a triangular notch. What is the discharge equation? 8 by 15 CD root 2g tan theta by 2 h raised to 5 by 2. In other words, your Q is directly proportional to h raised to 5 by 2. Okay. So next one, Cipolliti notch. Q is equal to 2/3 CD root 2g L h raised to 3 by 2. Again Q is proportional to h raised to 3 by 2. In all these cases, your Q directly proportional to the head you are going to measure over these notches. The question I am asking right now is, suppose if I do an error of say 1%, what is its effect on the discharge? I repeat, suppose if you do a mistake in noting down the head over a triangular notch, a rectangular notch or a trapezoidal notch, say 1%, then what is its effect on the discharge? That's what we are going to see in this case. We are considering for river level, we are considering two notches. One is a rectangular notch, the other one is a triangular notch. Let us see how to derive an equation for this effect on discharge over a notch due to error in the measurement of head. I hope this is clear. First, let us talk about a rectangular notch. Consider the discharge equation. Discharge equation is equal to 2/3 CD root 2G LH raised to 3/2. Now, 2/3 CD root 2G L is constant. I am going to replace that entire term by a constant K. Therefore, my equation reduces to Q is equal to, okay, so this K into H raised to 3/2. Again, this portion, remember, once you fabricate a rectangular notch, for that rectangular notch, CD is equal to constant. CD may be 0.6 or 0.65 or 0.62. So, 2/3 is constant, CD is constant, root 2G is constant. Once you fabricate, your L is constant. These are all constants. I am going to replace this entire term up to this point by this constant K. Therefore, this equation reduces to Q is equal to K into H raised to 3/2. Kindly recall, okay, what is your H? H is the head you are going to measure over the rectangular notch. Your head may be 1 centimeter, it may be 5 centimeter, it may be 10 centimeter, it may be 15 centimeter. So, this value of H varies from trial to trial, whereas rest of the things are constant. Okay. Now, consider this equation or call this as equation as 1. Now, differentiate this equation. Okay. We get this is dq is equal to K into this is 3/2 H raised to half into dH. Okay. So, with respect to which you are going to differentiate this? Differentiate this with respect to head. Okay. So, dq by dH is equal to, so K into 3/2 into H raised to half. If you rearrange this, you are going to get this dq is equal to K into 3/2 into H raised to half into dH. Call this as equation number 2. Now, divide this equation number 2 by equation number 1. So, here you have dq, here you have q. Now, dq by q is equal to, so write this equation by this equation, okay, you are going to get this form. If you simplify this, you are going to get this simplify form, this dq by q is equal to 3/2 into dH by dH. Again I repeat, if you simplify this equation, you are going to get the simplified form of this equation as dq by q is equal to 3/2 into dH by h. Call this as equation number 3. Now, what is the conclusion you are going to draw from this equation? It says that suppose if you do 1% error in measuring the head over a rectangular notch, remember this is 3/2, 3/2 is 1.5, okay, if you substitute 1% here, therefore my dq by q is equal to 1.5% error. What is the conclusion? If you made an error of 1% in noting down the head, the discharge is affected by 1.5%. That is what I mentioned in the next step. Above equation shows that error of 1% in measuring H will produce 1.5% error in discharge over a rectangular notch. Okay, that is the reason I said you need to be extra careful whenever you are measuring head over a notch. When you go to the laboratory, you must be very careful when you are doing these experiments. Okay. So, let us quickly see how we are going to derive this equation once again. It is a very simple derivation. Consider the discharge equation for a rectangular notch. 2/3 CD root 2G LH raised to 3/2. Now, 2/3 CD root 2G L is a constant. I am going to replace that by K. Therefore, my equation reduces to Q is equal to K into H raised to 3/2. I call that equation as 1. Now differentiate this equation with respect to h. Therefore, I am going to get this equation as dq by dh is equal to k into 3 by 2 into h raised to half. Remember, on the right hand side you have this h. When you differentiate that, that becomes 3 by 2 into h raised to half. Rearrange that, you are going to get this equation. So dq is equal to k star into 3 by 2 into h raised to half into dh. Call that equation as 2. Now divide equation 2 by equation 1. You are going to get this dq by q is equal to, okay. So dq corresponding to that, you have a right hand RHS terms, put the terms, and corresponding to this q you have the RHS values, substitute that values and simplify. You are going to get a simplified form of that equation. That equation says that dq by q is equal to 3 by 2 into dh by h. So the equation says that if you do 1% error in measuring the head over the notch, the error you are going to see in the discharge is 1.5%. This is for a rectangular notch. I hope things are clear. The same procedure we follow for a triangular notch. Let us see how much is the error in discharge if we do 1% error in measuring the head. As I mentioned, we will follow the same steps here also. First, consider the discharge equation for a triangular notch. Triangular notch is given by, the discharge equation for a triangular notch is given by 8 by 15 CD root 2g tan theta by 2 into h raised to 5 by 2. Now remember, CD, once you fabricate a triangular notch, CD is constant, the apex angle is constant. So in other words, 8 by 15 CD root 2g tan theta by 2 is constant for a particular triangular notch. So I am going to replace that by k. The equation becomes q is equal to k into h raised to 5 by 2. Now call that as equation number 1. Differentiate equation 1 with respect to h. If you do that, you are going to get this dq by dh is equal to k into, so 5 by 2 into h raised to 3 by 2. Rearrange that, you are going to get this equation 2, that is dq is equal to k into 5 by 2 into h raised to 3 by 2 into dh. This is my equation number 2. Divide equation number 2 by equation number 1, you are going to get this equation. Now if you simplify this, you are going to get an equation dq by q is equal to 5 by 2 into dh by h. Now what it says, suppose if I do 1% error in measuring this head over a V notch, the error incurred in this case is 5 divided by 2, that is equal to 2.5. In case of a triangular notch, if I do 1% error in measuring the head, then the error in the discharge will be 2.5%. In case of a rectangular notch, it will be 1.5% discharge error if we do 1% error in the head, and in case of a triangular notch, for 1% error there will be 2.5% error in the discharge. I hope things are clear. As I mentioned earlier, if you take out previous question papers, most of the time you are going to see problems on this finding the error. Let us see a couple of problems on this. You will get confidence how to solve this type of problems. Let us start with a simple problem. Water flows over a rectangular weir 1 meter wide at a depth of 150 mm and afterwards passes through a right angle triangular weir. Sir, you didn't start the weirs at all, now we are introducing weir in the problem. Absolutely not an issue. I am going to talk about the weirs in a couple of seconds or minutes from now onwards. Okay. So for the time being, so let us read this given problem as it is. So water flows over a rectangular weir 1 meter wide at a depth of 150 mm and afterwards passes through a right angle triangular weir. If you go to your laboratory, you are going to see this type of setup. Water first passes through a rectangular notch, then it flows over a V notch. Kindly recall, CD we defined as actual discharge divided by theoretical discharge. In order to calculate the discharge, in that case, we make use of this V notch. I know the coefficient of discharge of the V notch. Okay, if I measure the head over the V notch, okay, I can easily calculate what is the actual discharge flowing in the channel. In order to find the CD for this rectangular notch, I make use of this V notch in order to find the actual discharge. Probably once you go to the laboratory, once you see the models, you will appreciate what we are studying in the class. Okay, so take CD for the rectangular and triangular wear as 0.62 and 0.59 respectively. Find the depth over the triangular wear. Okay, so basically this problem it doesn't talk about the error. This is typically a lab problem. Okay, remember, whatever the amount of water that is flowing over the rectangular notch or a rectangular wear, the same amount of water is flowing over the V notch. Kindly recall law of conservation of mass or continuity equation. What it says? Q is equal to A1 V1 is equal to A2 V2. What is A1 V1 in this case? A1 V1 is the discharge over the rectangular wear. What is A2 V2? A2 V2 is the discharge flowing over the V notch. Again I repeat, the discharge flowing in the channel, the same amount of discharge is flowing over the rectangular notch, rectangular wear, and the same amount of discharge is flowing over the V notch. Based on that, we are going to find the CD or whatever the data that is given in the problem. Let us see how to solve this problem. First, note down what is the data that is given in the problem. So, what is the data given in the problem? First one, length of the rectangular notch or wear, L is equal to 1 meter. Then, depth of water over the wear, capital H is equal to 150 mm, convert that into meters, that becomes 0.15 meter. Coefficient of discharge for a rectangular wear is 0.62. Now, come to the triangular notch or rectangular wear. So, triangular wear is a right angle triangle wear, therefore, the apex angle is equal to 90 degrees. First thing, the coefficient of discharge for a V notch is 0.59. Okay. Now, let us see how to solve this problem. Now, the first step is, let the depth of water on the triangular wear be H1. Remember, the depth of water over the rectangular notch is 150 mm. This is 0.15 meter or 15 centimeter. Now, since we don't know what is the depth of water over a triangular wear, I assume it as H1. Now, the discharge over the rectangular wear is given by, write the formula, Q is equal to 2/3 CD root 2G L H raised to 3/2. Now, what is the data given in this? You know the value of CD. CD is 0.62, L is 1 meter, root 2G is constant and H is 0.15 meter. Substitute all these values and find the value of Q. So, Q is equal to, it works out to be 0.106 or it is 0.11 meter cube per second. Now, you know the discharge flowing over the rectangular notch. Just now I said, by continuity equation, Q is equal to Q1 is equal to Q2. Whatever the amount of discharge that is flowing over the rectangular notch, the same amount of discharge is flowing over the V notch. Again I repeat, Q is equal to Q1 is equal to Q2. Now, just now I computed the discharge over the rectangular notch. So, with that discharge, consider the discharge equation for a triangular notch or a wear. What is the discharge equation for a triangular wear or a notch? That is given by this Q is equal to 8/15 CD root 2G tan theta by 2 into H raised to 5/2. Just now you calculated the value of Q. So, in this case, if I talk about in terms of Q1 and Q2, this is my Q1 and this is my Q2, and Q1 is equal to Q2, that is equal to Q. Now, this is whatever the value you are calculated here, the same value substitute here. In other words, you know the value of Q. So Q is known, then 8 by 15, CD is given 0.59 then the problem, and it is a right angle triangle V notch. Therefore, my tan theta by 2 becomes tan 45. Tan 45 is equal to 1 into root 2g, again constant, into h, the unknown value. Okay, h raised to 5 by 2. Now, you can put this h as it is, or here also we use h, and here also there is no point in using the similar notation. You can change it to either small h, or you can call it as h1. That is what I did here in this case. In this case, I call this h as h1. Replace this capital H by h1, and if you simplify and find the value of h1, you are going to find the value of h1 is equal to 0.3572 meter. Again I repeat, the head over the V notch is 0.3572 meter. There are a couple of takeaways from this problem. What are the takeaways? Kindly recall what we discussed in the last class. Why V notches are preferred over other notches? One of the advantage I mentioned is, even for low discharges, the head over V notch is very high compared to other notches. Why? If you talk about a rectangular notch, if you talk about a trapezoidal notch, so you have what is known as a crust length or a sill length. Okay. Whereas if you talk about a triangular notch, the sill length is 0. In that case, whatever the area you are going to talk about, that will be dominated by depth. For example, if you talk about a rectangular notch, so the area of the strip is given by length into dh. That is, even the discharge is very small, it spreads over the entire rectangular notch or entire trapezoidal notch. But if you talk about a triangular notch, since the crust length is 0, okay, even for small discharge, you are going to see a huge depth. Now, if you kindly recall, or if you kindly look into what is the head over the rectangular notch here that is given in the problem. In the problem, the value of h given is 0.15 or 15 centimeter. So, Q is same. For this Q, the head over the rectangular notch is 15 centimeter. But if you allow the same discharge over the triangular notch, what will be the head? So, the head will be 36 centimeters, almost double what you measured on the rectangular notch. Then sir, what is the big deal? The big deal is measuring this accurate value of h is very easy when you have a high head. Just now we knew that if we do mistake in measuring the value of it, it directly affects the discharge. So, when the head over the notch is very high, we can take accurate values of head. I hope this is clear. Let us start with another problem. It is proposed to use a notch for measuring the water flow from a reservoir. It is estimated that an error in measuring the head above the bottom of the notch could be 1.5 mm. For a discharge of 0.3 meter cube per second, determine the percentage error which may occur. So, using a right angled triangular notch with coefficient of discharge of 0.6. What are the equations you need to remember? One is the discharge equation for a triangular notch. What is the discharge equation? Q is equal to 8 by 15 root 2g tan theta by 2 h raised to 5 by 2. That is the first equation you need to remember. What is the second equation? dq by q. I repeat, dq by q is equal to 2.5 times of dh by h. Again I repeat, if I do 1% error in measuring the head over a triangular notch, there will be an error of 2.5%. That is what we derived. Okay. Now, with these two equations, let us see how to find the how to solve this problem. Now, look at this. This is the equation for a triangular notch or a V notch. Now, for a V notch, the value of CD is equal to 0.6, that is given in the problem, and value of theta, it is a right angle triangle formula. Therefore, theta is equal to 90 degrees, apex angle is 90 degrees. Therefore, this reduces to, so in place of CD, substitute 0.6. So, tan theta by 2 becomes tan 45. Tan 45 is equal to 1. If you simplify this, you are going to get this Q is equal to 1.417 h raised to 5 by 2. Okay. Now, then read the problem once again. So, what is the discharge? Discharge given has 0.3 meter cube per second. And what is the value of H here? Here look at this. So, here the head above the bottom of the notch could be 1.5 mm. Okay. Now, consider this equation, dq by q is equal to, so 2.5 dh by h. Okay. Now, this 2.5 is constant into, so what is the error here? It is 1.5 mm. Convert that into meters. Now, what is the value of h? So, h is equal to, I think some data is missing in the problem. Kindly note down the value of h is 0.5374. Okay. Again, I repeat, the value of h given is missing in the problem. Kindly note down the value of h. Now, h is equal to 0.5374 meter, that is given in the problem. Now, if you know these values, so 2.5 into the value of this error is 1.5 mm, convert that into meters, and the value of h is 0.5374. Okay. So, here how you are going to find the value of h here? Now, look at this equation, q is equal to 1.417 h raised to 5 by 2. You know the value of q. Substitute the value of q here, corresponding to this you find the value of capital H. I hope the data given in the problem is perfectly alright. You need not have to bother about that. Again I repeat, get a general equation, write a general equation for this V notch, substitute the given values. So, what are the given values? The value of CD is 0.6, tan theta is 90 degrees, therefore tan 45 is 1. If you simplify this equation, you are going to get this q is equal to 1.417 h raised to 5 by 2. Now, q is given in the problem. So, substitute the value of q is equal to 0.3, therefore, find the value of h. If you find the value of capital H works out to be 0.5374 or it is 0.54 meters. Now, come to this general equation, dq by q is equal to 2.5 times dh by h. Now, h just now we calculated 0.54 and 2.5 is constant and dh by error is 1.5. So, convert that in meters. So, substitute this and find the error in the discharge. The error works out to be 0.7%. Okay. Again, a simple problem. Only thing is you must be little bit careful. You need to remember this formula and this formula. If you remember these two formula, this problem can be easily solved. Then we need one more, we solve one more problem, then we'll stop. A rectangular notch 40 centimeter long is used for measuring a discharge of 30 liters per second. An error of 1.5 mm was made while measuring the head over the notch. So, your dh is equal to 1.5 mm. So, convert that into meters. Calculate the percentage error in the discharge. Take CD is equal to 0.6. The earlier problem what we solved is for a triangular notch. Now, this is for a rectangular notch. Whatever the procedure we followed for the earlier problem, the same procedure we follow for this problem. So, probably within no time you are in a position to get the percentage error. Look at this, length of the notch 40 centimeter given, discharge 30 liters. Kindly recall 1 liter is equal to 1 by 1000 of a meter cube. So, convert that into meter cube or centimeter cube. Now, in this it is converted into centimeter cube per second. Now, error in the head is 1.5 mm, that becomes 0.15 centimeter. Coefficient of discharge is 0.6. Now, the discharge equation for the rectangular notch is given by 2/3 CD root 2G L H raised to 3 by 2. Now Q is given, so 2/3 is constant, CD is 0.6 given in the problem, L 40 centimeter that is given in the problem, and root 2G. Now we must be very, very careful here. So I kept everything in terms of centimeters. Suppose if you convert everything in terms of meters, here you must be very, very careful. This becomes 9.81. This is, you people most of the time you do in the mistake in the laboratory. You must be very careful when you are talking about the units. Either keep everything in terms of meters or everything in terms of centimeters. So keeping one in meters, the other unit in centimeters, no. It is not acceptable, and the value you are not going to get, value you are going to get is totally wrong. You must be very careful. Again, I repeat, either you convert everything in terms of meter or everything in terms of centimeters. So here in this problem, I kept everything in terms of centimeters, and if you solve it, you are going to get the value of capital H is equal to 12.16 centimeter, or it is 0.12 meters. Now, what is the equation? The equation is, remember, this is a rectangular notch. So what is the relation? If I do 1% error in noting down the head over the notch, so the error in the discharge is 1.5%. Therefore, dq by q is equal to, so 3 by 2 into, so dh by h. Okay, that's what I wrote here. So 3 by 2 dh by h. So 3 by 2. Now this is 15 mm, 1.5 mm. Therefore, that becomes 0.15 centimeter, and h just now you calculated it is 12.16. Substitute this value and you find an error of discharge is equal to 1.85%. Kindly recall, here the error is 1.5 mm. So this is the error I made in measuring the head. Now if I made this much error, its effect on the discharge is 1.85%. That's why this, you must be very, very careful whenever you are talking about this notches and wears, and whenever you are measuring this head over this notches and wears. So with this, we'll just have a recap of what we studied in this class. We started with stepped notch. We started with time of emptying a tank using a rectangular notch. Then we started with we studied about the error in the discharge. If you make 1% error in measuring the head. Then we solved a couple of problems. So I'll stop at this stage. We'll continue with some more topics on the same chapter in the next class. Thank you very much.